Another way to vary the notion of a graph is, again, by looking at the definition. So forget about digraphs, now we look at ordinary graphs. There we had a finite set of vertices and a finite family of edges. Now, of course, we can scrap this finiteness condition, and then if either of these sets is infinite, we talk about infinite graphs. We will not deal so much with infinite graphs in this course, so see this as some extra interesting piece of information, but just to let you know that these things exist. So a graph can be troublesome in many ways. A graph can be infinite in many ways. So you can have an infinite number of vertices, but a finite number of edges. Let me start you off. One example is the null graph on infinitely many vertices. It has infinitely many vertices and no edges at all. You can have the opposite. You can have a finite number of vertices and an infinite number of edges. You can have both vertices and edges come in infinite numbers, but if you look closely at each individual vertex, it will have finite degree. So there will be no vertex with infinitely many edges incoming. Or the worst case, you can have infinitely many vertices, infinitely many edges, and some vertices having infinitely many edges coming into them. So the exercise for you, if you're interested, is to construct one example of each kind. And just one piece of notation, a graph where all degrees are finite is called locally finite. So you might have infinitely many vertices and infinitely many edges, but if every vertex only connects to finitely many edges, then the graph is called locally finite.